So welcome back as we continue our discussion of power series. This is our third lesson on power series, and we're going to be talking about calculus with geometric series. Uh, as I've been introducing these lessons, I've been using this analogy of the power series as a multi-tool of calculus or of mathematics, and I realized that maybe some of you aren't really tracking what I'm saying with as a multi-tool. So I thought I would maybe compare a couple of things. So, for example, we have I've been using the crescent wrench right here, the little adjustable wrench, as opposed to a fixed jawed wrench. Ooh, I think I have one of those. Here's like a fixed wrench; it only fits one size, versus the crescent wrench, which is an adjustable size wrench. It can change sizes, right? So it's a multi-tool because it can be used for multiple sizes. Or I've had the little multi-tool cutter, which can cut or can do all kinds of funky little things. And I've even talked about the cell phone, which is quite familiar, although we don't often think about it as a multi-tool. Here's a more traditional one. I asked a colleague and he had one in the office, or actually in his truck, and graciously went out and got it. So this is a Leatherman. And so it opens up and it's pliers. And this is a new one. It's not mine, but it's got a little saw blade in it. And it's got scissors. What else is in here? Lots of stuff, right? A little blade. Looks like maybe a screwdriver, and there's probably a bottle opener and a few other things. It's a multi-tool, right? One little Leatherman can do a whole bunch of jobs, sort of like our power series. The one concept of an infinitely long polynomial can work in lots of different mathematical applications. Sometimes it can help to compare it to things that are not multi-tools. So I think about this one. So this is a staple remover, right? What's its job? It removes staples. Can you do other things? Well, if you're like me, you probably poked your fingers with it just to see what it feels like. But basically, it's got one job. It's a staple remover. Or how about this one? It's a pen. What does it do? It writes. Now, have we done other things with it? Yeah, we've poked things, measured, done a few other, used it as a stir stick or what have you. But basically, it does one thing and one thing only. It writes, and we hope that it does it well. Or how about this one? Scissors. You might say, well, it's sort of like the Leatherman, right? But the Leatherman had the scissors and a whole bunch of other things. The scissors basically does one thing. It cuts. These are the little kid scissors. They don't even cut very well. Every now and then, maybe you've been desperate, and so you've tried to use it to scrape or to do other things. But basically, what does the scissors do? It cuts. It cuts paper, tape, hair, not very much, right? It's just scissors. Or maybe a very valuable multi-tool. How about this one? The football, right? What does it do? Well, it's a ball. You play football. It's not even like a tennis ball where you could use a tennis ball for tennis or for baseball, or like you could practice other things. What can you do with a football? Well, you can pretty much play American football. That's about it, right? And so the power series is a multi-tool. Again, it's a multi-tool because the same thing, same little concept, the same little critter can be used for a variety of things. Just to clarify, this is not the best pair of pliers that's out here, right? It's not the best knife, but it's an okay pair of pliers. It's a okay knife, given that they're all in one little itty bitty package. Okay, so we're talking about the power series, and the key is that if you have this multi-tool, if you have the power series, we want to figure out how much can we get out of it. So in the last lesson, we learned about the geometric series. We learned about how to manipulate the geometric series using algebra. Today, we're going to learn how to manipulate the geometric series using calculus to get a whole bunch more out of that same one little formula that we have so far. Example 7, integrate the following. Integral of 1 over 1 minus 8x cubed dx.
So one thing you might notice is that we could integrate this using partial fractions. So we could factor, do a partial fractions decomposition, and see where that takes us. But since we're learning about a power series, let's take advantage of the power series. Remembering that we have, I think it was a green A and a yellow 8x cubed. So we see that this is of that form, 1 over 1 minus x, where in this case the x, or the yellow x, is 8x cubed. And so we could say the integral of 1 over 1 minus 8x cubed dx is equal to the integral of the sum from n equals 0 to infinity of, it's a little bit tough to read. Here's that yellow x, so to speak. So we're going to have 8x cubed. Oh, threes are having a hard time tonight, sorry. All raised to the nth power dx. Now, we haven't proven it yet. We haven't even really stated it yet, but proceeding as we would like to proceed, we could intuitively say, if I want to take the integral of this infinite sum, then that would be the same thing as finding the sum from n equals 0 to infinity of the integral 8x cubed all raised to the nth power dx. So that is the, the integral here of the sum is the same thing as the sum of the integrals. And I think we'll see a statement about this in a moment in the notes, but the main thing is that this is a true and valid statement provided all of these sums converge. So if we have nice x's, nice sums, then this is a valid thing to do. So notice from here that the, notice that 8 times x cubed all raised to the n would be 8 to the n x to the 3n. And 8 to the n is a constant, so this would be equal to the sum from n equals 0 to infinity of 8 to the n. Then we've got the integral of x to the 3n dx, which will be the sum from n equals 0 to infinity of 8 to the n times x to the 3n plus 1 divided by 3n plus 1. And all of this is going to be a plus c. It's tempting to write that plus c out here, but if we write it on the end, it's unclear whether that plus c is inside the summation or not. And so rather than writing it plus c at the end, in these kind of cases, it makes sense to put it as a c plus right at the beginning. So that's that's my constant of integration. And so the question asked us to integrate this function here, 1 over 1 minus 8x cubed. And we have integrated it. We have found an antiderivative, but we have a solution that is represented by a power series. Notice that when we have a power series, we also have to ask, when is this valid? So when is the statement valid? And so it will be valid. So this is valid, or it converges, when the yellow thing in magnitude, 8x cubed, is less than 1. Here's that yellow thing again. And in other words, that would be where the absolute value of x is less than 1/8. So we have a power series representation for our antiderivative. We found our antiderivative, way easier than doing partial fractions. It looks like it's just 1, 2, 3, 4 lines. But the kind of the funny part about this antiderivative is we've only got the antiderivative when x is between -1/8 and +1/8. So we've answered the question. I'm not sure how valuable it is, but nevertheless, we have answered the question. So we can begin to see the three main aspects of power series all coming together. So the first part is here. It's finding a power series representation for a function, and then we would use it to solve some question. So in the last example, we were finding a power series representation for the antiderivative of some given function. The second thing we have to do is we've got to ask what x values, for what x values is the power series representation? That is, when does the series converge or diverge? So for example, in the last example, we said that our power series was only valid between plus and minus 1/8. And then finally, we've got to prove that all this stuff is legitimate mathematics. And this last step is mostly beyond the scope of Highline math. We're going to touch on it a little bit. We will probably leave the finer details to another class, possibly a class well beyond Highline. So most of our effort is really going to be spent on these first two steps here of finding that power series representation and determining the x values for which the work is valid. As we assumed in the previous example, one of the qualities of power series is that they can be manipulated through addition, subtraction, multiplication, division, differentiation, and integration to find other power series. So for example, assuming the series behave nicely, that is converge on some neighborhood, we have the derivative of a sum is the same thing as the sum of the derivatives. So you can kind of move the differentiation in and out. Similarly, the integral of a sum is the same thing as the sum of the integrals. And it was this latter property that we used in example 7. Example 8, show that 1 over the quantity 1 minus x squared equals 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the fourth plus dot, 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 dot. This requires a little bit of cleverness. I think we could take it on from either side, the left side or the right side. But maybe we will take it on sort of looking at it from the left side and recognize that 1 over 1 minus x quantity squared looks a little bit like 1 over 1 minus x, except for the denominator squared. Rather than, we could multiply, but rather than, that's going to create kind of a nightmare. So rather than multiplying, let's see if we can create this expression through differentiation. So let's see. So let's notice that if you have the derivative of 1 over 1 minus x, this would be like the derivative of 1 minus x to the -1th. That will be negative 1 minus x to the -2th times -1 using the chain rule. Or in other words, 1 over 1 minus x quantity squared. So notice that the derivative of 1 minus x is 1 over 1 minus x quantity squared. So this tells us that the integral of 1 over 1 minus x quantity squared will be equal to 1 over 1 minus x. Okay. At least within a constant. So we can sort of go either way on this relationship. So if I want to use this, notice it's of course easier to differentiate than to integrate. Let's use this first step here. And the second one is just an observation. we won't need it at this time. So if I want to use 1, we notice that ddx of 1 over 1 minus x equals 1 over 1 minus x squared. But observe that ddx of 1 over 1 minus x is also equal to the derivative of the sum of x to the n, the geometric series. Shocking, isn't it? Geometric series comes up over and over and over again. If you want to differentiate an infinite series or a power series, you can differentiate term by term. So this is the sum from n equals 0 to infinity of ddx of x to the n, which would in turn be the sum from n equals 0 to infinity of n times x to the n minus 1. And if you wrote out the very first few terms, the very first term would be 0 plus 1 times x to the 0 plus n equals 2, so 2 times x to the 1 plus n equals 3, 3 times x to the 2 plus dot, 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 dot. Or in other words, we have 1 plus 2x plus 3x squared plus dot, 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 which is exactly what we were trying to show. Notice once again, this is all coming from the geometric series. Since it's all coming from the geometric series, this is only going to be valid when the absolute value of x is less than 1. Oh, and in case you were missing the connection between these things, this ddx of 1 over 1 minus x, that's the same thing as the 1 over 1 minus x quantity squared. So here's our power series that we've ended up with. So notice thus far we're mostly ignoring this question of when the power series are valid, except for the fact that these have all been related to geometric series, and so we actually have been able to answer the question at least a little bit at a time. Example 9, find a power series representation for ln of 1 minus x. So this is somewhat similar to the last example, except for in reverse. So here, notice that ddx of the ln of 1 minus x will be 1 over 1 minus x times negative 1, or negative 1 over 1 minus x. And so this tells us that the integral of negative 1 over 1 minus x dx will equal the ln of 1 minus x plus a constant. This thing over here on the left side, that's, well, at least inside the integrand, so it's this stuff right here, this stuff comes from the geometric series. So if we want to find ln of 1 minus x, we could take advantage of this time of line 2. Previous example was line 1. So this tells us that the ln of 1 minus x, which is what we care about, is equal to, there's going to be a constant of integration that we need to remember, c plus the integral of negative 1 over 1 minus x dx. So I've already accounted for the constant of integration before I started. I could add it in the end, either way. Here's our leading term of minus 1. Our common ratio is x. This is, shockingly enough, another geometric series. So we have c plus the sum from n equals 0 to infinity of -1 x to the n. Notice this would have to be true, and this would be when -1 is less than x is less than 1, or absolute value of x is less than 1. Okay. I guess I don't need to write the -1 here. So -1x would just be the same as just -x. Notice this is not alternating signs. Every single one of these terms is the same. A couple oddities of this. So if you look at this expression from -1 to 1, so think about putting in -1 into your ln. So at -1, this would be like ln of 1 minus -1, or ln of 2. And at 1, this would be ln of 1, which is, or ln of 0, pardon me. So this power series we're using is finding us values of ln between ln of 0 and ln of 2. Of course, ln of 0 is undefined. So in this particular case, we can actually find our value for c. So to find c, what we're going to, not next to c, next, find c. So to find c, what we're going to do is we're going to say these two expressions must be equal to each other, and so we can evaluate at some special value. So you might notice that if we let x equal it's going to be a little bit of a error. If you let x equal 1, oh, you can't let x equal 1. If we let x equal 0, I'm sorry. If we let x equal to 0, so let's let x equal 0, and then the two sides must be equal to each other. So if you look at this left-hand side here, the left-hand side, you're going to get left-hand side is equal to the ln of 1, which is 0. And then on the right-hand side, you're going to get right-hand side equals c plus the sum of the negative zeros, which is just 0. So you get 0 equals c plus the sum of the zeros. It should be clear from this that c is going to be 0, because you actually have an equivalence. So kind of cool. All told, we were able to find a power series representation for ln of 1 minus x. That power series representation we just found is that ln of 1 minus x equals the summation from n equals 0 to infinity of negative x to the n. And we've discovered that this c is 0 through this process down below. And we've also discovered that this power series is valid on that nice friendly domain absolute value of x less than 1. So historical note. Today we can evaluate logarithms simply by pushing a calculator button. But prior to having calculators, mathematicians looked up log values in books. And so one of the sources of the values in the books was that mathematicians would evaluate power series like the ones below. And so you'd have mathematicians, they would evaluate these power series over and over, not the whole thing all the way to infinity, but maybe the first 5 or 10 terms, just enough to get with the answer they needed. And they would create a value, and then they would look up and they'd find another value. And so they create these tables that could be used. And you can find them, go look at a thrift shop for an old CRC handbook, for example. and that'll show you tables of logarithms. In example 10, we want to integrate the inverse tangent of x using power series. And we could evaluate this using Calc 2 techniques by, I believe, using integration by parts. But here we're going to use power series. And to do that, we're going to remember that kind of a relationship. So recall that the derivative of arctangent is 1 over 1 plus that argument squared. Well, this quantity here, the 1 over 1 plus x squared, might look familiar to you. You might remember it from earlier in this lesson. So from example 6, we had that 1 over 1 plus x squared is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n, like that. And so if this is the derivative of arctangent, then that tells us that arctangent must be the antiderivative. So arctangent must equal the integral of 1 over 1 plus x squared dx, or in other words, the integral of the power series from n equals 0 to infinity of negative 1 to the 2n dx. Well, that puppy is, we can pull the summation outside, the sum from n equals 0 to infinity of the integral, ooh, I lost an x. Oh my gosh. Sorry, I got a copy error here. Negative 1 to the n, x to the 2n. So integral from n equals 0 to infinity of negative 1 to the n, x to the 2n dx. So this would be c plus the integral, or the sum from n equals 0 to infinity of negative 1 to the n, since that's a constant, times x to the 2n plus 1, all over 2n plus 1. Notice this needs to be true for all x's. And so to find c, so let's see, find c. So to find c, we can set x equal to 0. And so we know that the arctangent of 0 is 0. And over on the right side, we notice we have a sum of x to the powers. And if we let x equal 0, we'll get a sum of a whole bunch of zeros. And so on that right side, on the right-hand side, we will get c plus the sum of the zeros again. And so since these two things must be equal to each other, we get that c equals 0. So we're not done yet. Okay? All we have shown so far is that the integral of the arctangent of x dx, which is the question we're trying to answer, would be the same thing as trying to find the integral of the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 dx. And so you might say, where is that coming from? So we showed that arctangent of x is equal to all of this garbage down here, the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1. Remember, c is equal to 0. And so we're going to replace the arctangent of x in the integral that we care about with the summation we found above, or that we've already found. And now we can find the integral of the sum is the same as the sum of the integrals. The -1 to the n remains a constant. And so now we're going to we'll have a new constant. Maybe I'll call this one C1. And it's going to be the sum from n equals 0 to infinity. Still, we've got a -1 to the n. And now we have an x to the 2n plus 2 divided by 2n plus 1 times 2n plus 2. And in this particular case, we're no longer going to be able to just get rid of that constant of integration, find out what value it is, because since we have an improper integral on the left, it makes sense that we will have an improper integral on the right, complete with that constant of integration. So is this better? Is this worse? I'm not exactly sure, but this would be an example of how you could find an antiderivative instead of using the integration by parts. You could do it using power series. I should also comment that this is valid, or it converges, when absolute value of x is less than 1. And the reason I know its absolute value of x is less than 1 is because this formula that we're using is coming from a geometric series that had that same interval of convergence. So as the historical note says, earlier in calculus, we learned to integrate questions like this using integration by parts. Power series provides an alternate approach that requires no calculus skills beyond integrating and differentiating polynomial terms. And so you can imagine, here you are able to integrate things without knowing more sophisticated integration techniques. Pretty interesting and somewhat valuable.
So in this lesson, we learned how to use calculus, namely derivatives and integrals, along with all of our algebraic manipulations, to be able to find to be able to stretch that power series even farther. It reminds me a little bit about how you get a new tool, maybe you get a cell phone, and then at least for me, I'm perhaps a little older than you, but then I learned about apps. And I'm like, oh, I could have all my base things, but then I could download an app to be able to get more out of this multi-tool. So one of the apps that we use with our power series, multi-tool is, we're like, oh, I've got the derivative and integral app, and I can like manipulate them to be able to get more power out of the same tool that we have here.